Hi everyone, this is Steve Smith back at the SPARQ Observatory, and today I'm going to present in this video what I consider to be a pretty reasonable astrophotography workflow. This is going to involve a couple different sections that I've divided up into specific steps, and I'll go through each of the sections and then I'll go through each of the steps pretty quickly and then give you a list at the very end of all the steps that I use in a workflow. And all the steps that are in the workflow, I have also made other videos for each specific one to get into the details of how to actually accomplish a particular process. So to begin, the first section that I want to talk about is just image acquisition, and this is simply taking pictures with the telescope and the astronomical camera, astrophotography camera. And there are two types of images that we take. We take raw images and calibration frames. So the raw images are the images of your target, your galaxy, your nebula, globular cluster, whatever it may be. But along with that, we have to take calibration frames, bias frames, dark frames, and flat frames to deal with noise and other issues in the optical train. And so those need to be taken or should be taken at roughly the same time as the raw images are. So those two types of images, raw images and calibration frames, and then there are three different types of calibration frames. And that's it for image acquisition. Once you have all those files, then you can start to go into the processing flow to make an astrophotograph. And I've divided the processing up into two sections. The first one is linear processing, and these are steps that maintain the proportion of pixel values to the number of photons. So when photons come through the telescope and strike the camera chip, they're striking specific photosites. Those get, you can think of those as pixels when they come out on your computer screen, but on the CCD chip themselves, they're photosites. And when a photon hits a photosite, it discharges an electron, and that changes the charge in that particular pixel. And what we want to have is we want to have values when we go to the computer and the processing. We want to make sure that our pixel values are proportional to the number of photons that have hit that photosite. So this is a very, very simplistic example. So for those of you that may be more experienced astrophotographers, take this with a grain of salt, but I think this will get the point across. Let's say that we have one pixel, and over a period of time that the shutter is open, it's received 25,000 photons, and one right next to it has received 60,000 photons. And so the one on the right, since it's received more photons, when it shows up on your computer screen, is going to be displayed as a brighter pixel. So when we go into Pixinsight is going to map all the pixels and scale all the pixel values between 0 and 1. So as an example, it might just take, it's going to depend on what the high and low values are for the entire image. And so for our camera at the SPARQ Observatory, that's well over 6 million pixels. So it's going to determine all these specific pixel values based on the photons that have struck it and proportion them out between 0 and 1. And so let's say that the photosite that received 25,000 photons is interpreted by Pixinsight as a pixel that is ranked at 0.25, somewhere between 0 and 1. And that would mean that the pixel value for the photosite that received 60,000 photons would be 0.6. This maintains the proportion of pixel value to the number of photons that originally hit the photosite in the chip. Okay, so if we were to graph this, if we were to graph pixel values against the number of photons, we would have a straight line. If we mapped every pixel value for every pixel in the image, measured every pixel value, mapped the number of photons, we should get a straight line. It should be every pixel should be proportional to all the other pixels in the image in terms of the number of photons that have hit it. Well, let's say in the journey of our astro processing, we decide that we want to create a little more contrast between those two pixels. And so we'll take the pixel on the left and make it a little darker, and the pixel on the right and make it a little brighter. And now let's say that Pixinsight is assigning these pixel values, 0.05, so significantly darker than the original 0.25, and 0.9, significantly brighter than the original value of 0.6. We have more of a contrast. But remember, we're not actually adding photons to the, we're not taking the photo and taking it and throwing it back into the astrophotography camera and gathering more photons from our galaxy or nebula or whatever. We're just doing this in processing. And so at this point, we still have the original 25,000 photons for the pixel on the left and 60,000 on the right, and we have destroyed the proportions that were originally there. Once you get to this point, you are now doing non-linear processing. And if you were to take a graph of this, you would no longer have a straight line. You'd have some sort of curved arc, something like this. So that's the difference between linear processing and non-linear processing. Is linear processing, you're maintaining the proportion of the number of photons that have hit a photosite to the pixel value. And nonlinear, you are stretching that, you are destroying that. So the original data is essentially wrecked. And for astrophotography, you absolutely have to do this. For photometry or for some other research where you're trying to get actual real data, you would never, ever do nonlinear processing. You want to deal with the real data that's there. But for astrophotography, this is an art and a science. So we get to do a little science and then we get to mess around with it in art, and that very well will mean that we are going to destroy that proportion. So I want to divide the workflow up into these three areas: image acquisition, linear processing, and nonlinear processing. So let's take a look at the other areas that I like to look at. If you've looked at the video that I made called Principles of Astrophotography, you know that I'm primarily concerned with these four areas: getting enough light in our image to where we can actually see something, trying to reduce the noise in the image that can result in a lot of graininess, and where pixel values right next to each other are kind of inconsistent, and we want to kind of smooth that out and reduce that if we can. We want to bring out as much detail in the object as we can so that we can actually see interesting features of the galaxy or the nebula or whatever it may be. And of course, we want to have some color in our image. Color looks good to the eye, and it can also reflect some actual physical processes that may be going on in the object that we're photographing. So along with the three basic areas I'm going to be talking about: image acquisition, linear processing, and nonlinear processing, I'm also going to be talking about these four areas: light, noise, detail, and color, and which ones are affected by which process. Which process, there might be a process that deals with just noise and a process that deals with just detail, or maybe some combination of those, and I'll be including that in this video. Let's talk first, as we should, about image acquisition, just really quick. So in image acquisition, at SPARQ we have our regular LRGB filters, lumen, which is the entire visible spectrum, red, green, and blue, red being lower energy, green in the middle, and blue high energy. And then we also have two narrowband filters, hydrogen alpha and oxygen 3, O3. Hydrogen alpha falls in the red area, red wavelength, and O3 falls kind of roughly right between the green and the blue, but we tend to process it with green. So we have those 6 filters that we can use. You can also just use the LRGB and not worry about the narrowbands if you'd like to do that. We want to take a lot of raw images. So you'll be taking 100 or more, maybe several hundred images with these different filters. Not several hundred lumens and several hundred reds, but I mean several hundred images all together. And of course, we'll be taking our bias, dark frames, and flat frames at the same time. Usually Mr. Kruger and or myself will be taking those, and we'll make master calibration frames for you to use. And when you take your raw images, what you're really dealing with is you're gathering a lot of light, and the more raw images that you take, you're going to be overall reducing the noise when we start to put them together. So if you only take a few images, you're not going to have much light, and the images that you do have, when we combine them, will have a lot of noise. So we want to take a lot of images, raw images. And then when we apply the calibration frames are mainly there to help reduce the noise in the readout from the camera to the computer, the noise that happens in the chip itself when the shutter is open for a long time. Some of the photosites can get overcharged and appear more white than they should, so they can be counted as photons when it's not really photons that are hitting the camera. And so we want to essentially make a map of that. That's a dark frame. And then a flat frame, which is a picture of the optical train, including all the glass and mirrors and the glass that's on the filters, any scratches, dust bunnies, etc. And so, again, I mentioned this in the Principles of Astrophotography. A flat frame really isn't dealing with noise so much as it is just kind of defects in the optical train. But bias frames and dark frames do directly reduce noise in your image, electronic noise and thermal noise. We do want to make sure, again, that we take the calibration frames at the same time that we're taking the raw images, as close as possible. The big observatories, Mauna Kea, observatories down in the Atacama Desert, they will be taking calibration frames pretty much every night to go along with the images the raw images that they're taking. All right, before we get into the actual processing, there is one intermediate step. After you've taken all your raw images, we do have to go through them. And so we have to approve images and send them on to the next step, because some images, you may have had clouds come over or a plane or a satellite right through the middle of your galaxy or whatever, and we can't use those. So we want to make sure that we send on images that we approve. And also, we want to select the single best image from each filter. So the single best lumen image, single best red, single best green, blue, etc. We need to do that for integrating the images when we make a single master. We want to pick the best one as a reference image from each filter. So most of our processing is going to be done in Pixinsight. And for image approval and selecting the best images for each filter, the first thing we're going to use is the subframe selector, and we will load all the images from just one filter, say like all the lumens in there, and look at what we have. Look at the number of stars, look at the signal to noise ratio, look at the full width half maximum. We may look at some other things to determine what images are good enough to be used in the process to get to our final image. So that's the subframe selector. And as we go through the subframe selector, it's not directly processing any images, but it is selecting images for light and for good signal to noise ratio, and also for detail. It will help with all these using the subframe selector. So that's in Pixinsight. That's the first thing that we do. But again, that's not really processing any images. That's kind of getting us prepared and set up to process images. So that takes care of our image acquisition. We don't have to do much with that aside from take the raw images and calibration frames. And now we're ready for processing. And we're going to start with linear processing. So again, this is preserving the proportion of pixel values to the number of photons. We'll get into nonlinear processing closer to the end of the workflow. So in linear processing, the first thing we want to do is apply the calibration frames. Those are the bias, the dark frames, and the flat frames to the raw images that we have approved. We're going to use Pixinsight, and Pixinsight has a tool called image calibration. So you will load your raw images from a single filter, so all your lumens, and then maybe all your reds after that. And you will apply the correct bias, dark, and flat frames to the image calibration. And image calibration, again, is mainly used to deal with the readout noise, which is what the bias frame addresses, the thermal noise, which is what the dark frame addresses, And then finally, any defects in the optical system, dust bunnies, scratches, etc. in the mirrors and the glass, and that's what the flat frames do for image calibration. So we get done with this process. We have raw images that have now been calibrated. Next step is to correct for the remaining hot and cold pixels. So Pixinsight does a pretty good job, especially if you've done a good job taking your calibration frames and applying them properly, of getting rid of any hot pixels and cold pixels, but we may still have some left over. So we use a process in Pixinsight called cosmetic correction. And again, that'll just kind of deal with a little bit of extra noise if we have some that is left over from calibration frames. The next step is we will take all of our images and we will align them to a single master. So when we do the subframe selector, we're going to select a single lumen image, and we're going to have all the other images, regardless of what filter was used, aligned to those. So all the star fields, all the stars will line up on top of one another. And again, this is in Pixinsight, and we use a tool called star alignment. And again, this is also called registration. You may have heard it be called that. And there is no processing with that. It's just kind of getting all the images to line up. So there's nothing that you're actually doing to the images, although some of the edges get cut off when we do that. The next step is within each filter. We would take all the lumen images, for example, and stack them, creating a single image. So we take all the lumen images we have and we crush them together and make one master lumen image. We'll do the same with the reds, make one red image, same with the greens, etc. That's in Pixinsight. This is called image integration, also called stacking. And this deals with 3 of the 4 things that we are interested in. It's going to give you a lot more light. It's going to give you a lot more contrast. It's also going to bring down the noise somewhat, because the signal to noise ratio for the stacked image is going to be higher than any of the raw images. And because of that, you're going to get more detail in your master. So if you look at just a single raw image of a lumen frame, and then look at the master image that may be taken with, let's say, 50 lumen frames, you're going to see a lot better light, a lot less noise, and a lot more detail. Next step, we're going to crop the master images to eliminate the bad edges. Because we dither the telescope, move the telescope a little bit between each image, and also we have a German equatorial mount, which means it flips between going east to west. And so we end up, when we align all the images to that one lumen image that we selected, we end up with some bad edges, some edges that are black. And so we need to crop all the master images in exactly the same way so that we eliminate those bad edges. And yet we want to be careful to crop so that we don't lose our alignment, so that all the masters still line up on top of one another. And in Pixinsight, we have a tool called dynamic crop that does this for us. Again, it's not really processing things in terms of bringing out detail or doing anything with color or noise or anything like that. It's just to get rid of the edges that we don't want to use. Now at this point, we have to process the lumen separately from the color filters that we have. And even though some of the processing is the same, we do want to separate it out and just address the lumen. Now you can address the color ones first. You don't have to address the lumen one first. I tend to do the lumen first and get that out of the way and then deal with color. So for the lumen processing, we start with evening out the background sky. And so we can have some gradients or whatever. Gradients is where maybe one side of the image is a little bit lighter or a little bit darker, or a corner is a bit lighter or darker. The background sky is uneven. And so we use a tool in Pixinsight called automatic background extraction. And it sort of, I put noise here because it sort of addresses the noise in the sense of that it kind of, because it evens out the background sky, it is kind of addressing noise somewhat. Now it may actually, in some cases, be adding some noise if it's looking at the background sky and putting some more noise in to even it out. But a lot of times it's going to take some noise out. So either way, noise is affected, background sky noise is affected by using automatic background extraction. But the goal is to get the background sky even. So once the background sky is even, it's a lot easier to deal with the background sky as a whole, rather than having to deal with it in little sections that are not consistent with one another. So we want to get the background sky consistent. Next up, after we have the background sky done, is deconvolution. As a lot of you know, when light comes through the atmosphere, it gets diffracted and spread out. So when it hits our camera chip, our galaxy, our nebula, the stars kind of get smeared out a little bit, and we want to compensate for that, and we have a process to do that. In Pixinsight, this is Blur Exterminator, which is a third-party tool by RC Astro, Russell Croman, and does a great job of bringing out detail in our object. Also makes the stars a little bit smaller and doesn't leave artifacts, which is great. So this is a wonderful tool, and compensates for all the atmospheric problems that we have when light comes through the atmosphere. Next up, we have noise reduction. So in Pixinsight, we can use either Russell Croman's noise exterminator or the multi-scale linear transform. Either one of those are fine. And since we're dealing with noise reduction, obviously what we're affecting is the noise. We're trying to crush down the noise, especially in the background sky, all the graininess. We want to try and get a lot of that smoothed out as much as we can. Okay, so that's the linear processing for the lumen. We do have one last thing to do with our lumen, and that is a nonlinear process. So this is when we're going to destroy the proportional value of photons versus pixel values. And that process, this is the last thing that we do with our lumen before saving it as our lumen master. And we want to enhance the contrast and detail and crush down the noise. And we use the histogram transformation in Pixinsight to do that. This deals with all three of the areas that we're dealing with in Lumen. And Lumen is essentially grayscale, black and white, if you want to think of it that way. And we're dealing with light, noise, and detail. So the histogram transformation is the tool that we use to really work on all of these. So the light, we can make sure that we can see our object. The noise, we've crushed down the background noise, the background sky noise. And detail, if we're doing a galaxy, maybe we want to see a dust lane. If it's a nebula, maybe we want to see some globules or something in the nebula, some nice edges. There's lots of stuff to see. We want to make sure that we bring the detail out, and histogram transformation can do all that. Okay, so back to our linear processing, but now we have to deal with the color filters, and this is a bit more involved. So we're going to start. We're going to call this RGB, but we're going to start. If you've done hydrogen alpha and O3, if you use those filters, we have to blend those in with the red and the green. Hydrogen alpha into red and O3 into the green. And we use a whole series of formulas and math in the Pixel Math tool in Pixinsight to do that. You don't simply add hydrogen alpha and red together, and you don't add oxygen 3 and green together or multiply them or anything like that. It's a bit of a process because you want to make sure that you're getting the best of both of them, not just a simple averaging. So this will bring out a lot of detail. So hydrogen alpha can bring out a lot of detail in your red image. O3 can bring out a lot of detail in your green image. And of course, we're dealing with color at this point, although we don't see color quite yet. But we are going to be affecting the color by doing this blending. And if maybe you've just done RGB without the narrowband, that's fine. And if you've done the narrowband, you've now combined them in so that we do have a single red image, single green, single blue, whichever way you did it. And the next thing to do is to combine these into a single RGB image. And for Pixinsight, we use channel combination, and that obviously gives us color. So what happens in this process is Pixinsight will assign red to what you're calling the red master. it'll assign the color green to the green master and blue to the blue master. And this will be the first time that you actually see some color in the image. Up to now, everything's been black and white. So this is kind of an exciting moment, hopefully. A lot of times we end up with a really messy color image because we have lights around the observatory, parking lot lights and stuff like that. With that, we can't do anything out. Apparently the district frowns on us trying to take the lights out, so we don't do that. So we end up being able to do this in processing. So first time we get color, and let's see what happens next. Next step is we're going to even out the background sky. If this sounds familiar, it's because we did this with processing the lumen, and we're going to use the same tool. We're going to use Pixinsight's automatic background extraction to even out the background sky so that the noise in the background sky is pretty much the same everywhere, so we don't have to deal with separate sections. Next up, we're going to obtain the right ascension and declination of the image. And you may be thinking, why do we have to do that? We're not doing, we're not like trying to measure where things are really. We're trying to make a nice photograph. Well, we need to do this for a process that we're going to do right after this. And so we're going to use Pixinsight's image solver to get the right ascension and declination of the center of the image and the pixels in each of the corners. So we're going to have 5 different right ascension and declination locations for the image that Pixinsight will put in the metadata for the image. And so the reason that I've put color here and in parentheses is we're not really doing anything with color with this process, but we need to use the image solver for the next process. We need the results of the image solver for the next process. And what we want to do next is obtain the correct color. So even though we've combined the red, green, and blue and we have some color, we don't know for sure if it's the correct color. So we're going to do a spectrophotometric color calibration. This is a tool that Pixinsight has. And the way that this works is Pixinsight uses star data from the Gaia satellite, and Gaia knows the temperature and colors of all these different stars. Pixinsight maps our image onto the Gaia database, and the only way it can do that is if it knows the right ascension and declination of the center of the image and the corners. So once it does that, then Pixinsight can figure out what stars are in our image and look at Gaia's data that it has for what color those stars should be, and it makes a calibration of the color in the entire image based on what it based on the math that it does. The difference between the stars that we have, the color of the stars that we have versus the color that they should be. So this definitely picks up the color quite a bit, and that's why I have color highlighted there as what we're dealing with. And then here's a repeat from Lumen. We want to do some deconvolution, again compensating for atmospheric diffraction, and we're going to use the same tool, Russell Croman's wonderful blur exterminator. And even though in an astrophotograph we get a lot of the detail, most of the detail out of the Lumen image, there's no harm in getting some detail out of our RGB as well. So we're going to apply blur exterminator to the RGB as well. And the next process after that is noise reduction. This also should sound familiar because we did this with the Lumen image also, and we're going to use the same tool, either noise exterminator or the multi-scale linear transform, and this is going to knock down the noise, especially in the background sky. And then finally, just like we did with the Lumen, we have to do our last step with our RGB image, which is a non-linear processing. And it's the same one that we use for the Lumen. It is to enhance the contrast and detail, crush down the noise a little bit more. We're going to use the histogram transformation tool in Pixinsight, and it's going to deal again with light and noise and detail, not color, because the color's already kind of in the image. We're just kind of bringing out where those colors are and crushing down the noise. Finally, we've got a lumen master and we've got an RGB master, and we're going to put those together to make a single LRGB master, and this will be the single image that we work with for the rest of the process. And we're going to use Pixinsight's LRGB combination tool, and particularly light, detail, and color. We're not really working with noise here, but when we combine these images, the lumen image is going to bring a lot of light and detail into our LRGB master, and of course the RGB is going to provide the color. The next step in our nonlinear processing, now that we've just made our LRGB master, is we want to bring out a little more contrast in the image, a little more difference between light and dark, and we use a tool in Pixinsight called Curves Transformation, and that's going to deal with both light and detail. You may also note that everything now is nonlinear because we already destroyed the linear processing when we did the histogram transformation for both the lumen master and the RGB master. So everything at this point, we're already dealing with nonlinear processing. The next thing we want to do is enhance the contrast. So we want to see more of what we want to see and less of what we don't want to see, essentially. And we want to see more details. So one of the tools we can use is the local histogram equalization. And this is a tool in Pixinsight that looks at specific blocks of areas in your LRGB image and adjusts the histogram to make some more contrast. This primarily has to deal with light and detail. Next, if we have something where we want to enhance the contrast in the darker areas, Pixinsight has a tool for that too. Because sometimes the darker areas, it doesn't seem like there's much going on, but you can have some contrast in there, and you might want to bring that out a bit. And in Pixinsight, there's a script called Dark Structure Enhance, and it will look at just the darkest areas of your target and make some more contrast with the light, and that obviously is going to bring out more detail in the dark areas. And then the last thing we need to do in Pixinsight before we run it over to Photoshop and mess with it over there, Photoshop does not recognize, won't recognize the Pixinsight file format, which is .xisf, and we need to put it in a format that Photoshop will recognize, and so we save it from the Pixinsight file format to a TIFF file format, 16-bit. Continuing on with our non-linear processing, next thing we want to do is repair bad pixels. And so we want to go through the entire image. We want to zoom in on the entire image and go through it very carefully and see if there are any pixels that we missed. Maybe there are some hot pixels or cold pixels that didn't get taken out during our calibration frames or cosmetic correction or some other work that we've done. And so we have a chance in Photoshop to do this. And we can use the healing brush or clone stamp to do that. And so if we find a bad pixel, we can replace it with pixels that are surrounding it pretty easily in Photoshop. And so this is both a light, a detail, a noise, and a color issue. So if we're going to replace a pixel with the average of neighboring pixels, it's going to deal with all of these. If we have a pixel that shouldn't be there, that's a detail that we don't want. So we would get rid of that detail. It's going to put in the color of the surrounding pixels, and if it also comes off as noise, it's not going to look like noise anymore because it's going to match the surrounding pixels, and of course that's obviously going to affect the light of that pixel as well. So repairing bad pixels actually deals with all four of these areas. Next up, we're going to darken and blur the background sky using some tools that Photoshop has, where we'll use a selection tool to work on just the background sky, and if it's pixelated, we can blur it, we can lower the contrast, and we can lower the saturation. Sometimes the background sky can end up having a green tint to it, a very slight green tint, and if we lower the saturation, lowering the saturation essentially means whatever color is in there, we're going to kind of wipe the color out and just make it grayscale. We can get rid of those tints if we have any. And we also, again, want to lower the contrast. We don't want a bunch of graininess, and the blurring will also help with that. So darken and blurring the background sky in Photoshop. Deals with light, noise, and color. The next thing that we're going to do in Photoshop is we are going to, if we need to, enhance the contrast and detail. And in this we're going to use a high pass filter mask. So both Photoshop and Pixinsight allow you the use of masks, which is something that you can work on only a part of the image, a specific part of the image that you select through different processes, so that you're not affecting the entire image, you're just working a part of it. So if we want to enhance detail in, say, like a spiral galaxy or something like that, we can use a high pass filter mask to essentially just paint in the areas where we want to bring out more detail. And this will change both the light and the detail in our image. Next up, we want to smooth any artificial edges. Sometimes some edges can show up with some of these processes, and we also have another opportunity to reduce noise here. And in Photoshop we can use another mask. We can use a blur mask, and that will reduce some noise and also reduce the color or change the color somewhat, so it's not as prominent. And so the using a blur mask for some things is really useful if we still see some things that are that we don't want to have quite in the forefront. Next up, and this is the last process that I usually do, I want to enhance the color. And so sometimes the color can seem a little bit washed out, and maybe I want to make the color a little more lively, bring some things out. And in Photoshop we can use a saturation tool and what Photoshop calls a vibrance tool to make some of the color pop. Again, you can do this with a mask, or you can do this for the entire image. We'll talk about that in the video that specifically addresses saturation and vibrance. Okay, so that is my process, and I want to kind of review each of the steps rather quickly and kind of put them all on just one slide here so you can see them all at one time if you want to make a copy of them. And so again, we're talking about three areas: image acquisition, linear processing, and nonlinear processing. And for image acquisition, we're just talking about taking the raw images and taking the calibration frames, those two things. In linear processing, or I should say before we get to linear processing, we do have that one step that we have to take, which is to approve images that we want to continue on working with and select the best image for each filter. And in linear processing, we want to apply calibration frames, cosmetic correction, registration, lining all the images up on top of one another, stacking them so that we have one master image for each filter, and then finally cropping them to get rid of the bad edges. So we're going to look at our linear processing, and just for the lumen image. So at this point we're going to just be dealing with a single lumen image that we've made from stacking. The first thing we're going to do is even out the background sky by applying automatic background extraction. Then we're going to use Russell Croman's blur exterminator to bring out detail, his noise exterminator, or we can use Pixinsight's native multi-scale linear transform to crush down the noise. And then finally, nonlinear processing, we're going to destroy the proportion of photons to pixel values using the histogram transformation, and that's going to address a lot of issues with our image, bring out some detail, lessen the background, etc., etc. And so that's for the lumen. At this point we have a really nice, should have a really nice lumen master. We're going to go back to linear processing, and now we're going to address our RGB image that we have. And we actually don't have an RGB image. We have separate red, green, and blue. And if we've used hydrogen alpha and O3, we need to blend those in. Again, hydrogen alpha goes into the red, and O3 goes into the green. Then we use channel combine. And so Pixinsight has a tool that allows us to put the red, green, and blue masters together to make an RGB image. And then we're going to be copying some of the same things that we did with the lumen image, evening out the background sky with automatic background extraction. We're going to adjust the color by using the Gaia data from its star temperatures and color that it has to match what we have in our image. And it will calibrate our color for our image. Russell Croman's Blur Exterminator, bringing out some detail. Noise Exterminator, again, our multi-scale linear transform to crush down some noise. And then finally, the last thing we do with our RGB master is to do a nonlinear process, which is histogram transformation. Same thing as we did with the lumen. So the next thing that we need to deal with is putting the lumen together with our RGB so that we have an LRGB image, and that involves just doing an LRGB combine. Then we'll use curves transformation, local histogram equalization, dark structure enhance. We'll save it as a TIFF. This is all in Pixinsight. And then we will, in Photoshop, do pixel repair, darken and blur the background sky, enhance the contrast and detail, smooth the edges, reduce the noise, and finally enhance the color. And finally, here is a complete list of what I consider to be a pretty reasonable workflow. Obviously, it's not as much as the professional astrophotographers out there, but I think it does a pretty good job overall, and isn't a really huge time suck. I think it does a pretty good job overall. So again, the first two steps, take raw images and take calibration frames. That's part of image acquisition. Then starting with step 3, we're working in Pixinsight. And eventually we're working with all the images in Pixinsight, and then we eventually get to the point where we just are going to be working with a lumen image. And that starts at step 9 and goes through 12, and then starting at step 13, we are dealing with our RGB image. And then if we continue in the next column, working with the RGB down to step 19, the histogram transformation. And again, step 12 and step 19, the histogram transformation in lumen and in RGB. This is when we go from linear processing to nonlinear processing, disrupting the proportion of photons to the pixel values. Step 20, we start working with our LRGB master image, which is the last image. We've started out with maybe 100 or 200 or 300 images, and now we're down to just working with this one image that we've created out of all those others. Eventually we get to step 24 in Pixinsight, where we're saving it as a TIFF, and then everything else, the last few steps, so we kind of clean some minor things up if needed in Photoshop. So that's the workflow that I have. There are plenty of workflows online that other people have, and it's always a good idea to go on there and look at what other people do. Always great to see some discussions about what order things should be in and why things are the way they are, and et cetera, et cetera. Always good to expand your knowledge. So I would encourage the students at SPARQ to do that. And if there are members in the public out there listening to this, I would hope that you would do that too. This is just one approach, my approach that I do with the students at the SPARQ Observatory. And again, this is Steve Smith with our astrophotography workflow. Good luck with all of your astrophotography, and I will see you next time.